Hey BC Cal students, this video is for the mixed review that we did for sequences and series. We took out a lot of questions that dealt with the limit comparison or direct comparison test. We'll go back and add those in, and I'll make a video that explains those concepts. I omitted them because they were not on this year's test, but it's still relevant knowledge and might be useful for next year. All right, so for number one, we have this function f of x is 1 over x squared plus 9, and we need to evaluate the improper integral or show that the integral diverges. So we're going to do this on a separate sheet of paper. So for number one, what we're integrating is we have this integral from 3 to infinity of 1 over x squared plus 9 dx. And if we integrate that, this is just the inverse tangent formula. So we touched on briefly the antiderivative of du over u squared plus a squared, that's an a, is 1 over a tangent inverse u over a. That's just a formula for when we have an integral in that form. So in this case, we end up with 1/3 tangent inverse with x over 3. And we're evaluating that from 3 to infinity. So when we did improper integrals, now again, that's something we also touched on briefly because of coronavirus and all this stuff. We said that when you have an improper integral, you can rewrite this as the limit as b approaches infinity of 1/3 tangent inverse of, in this case, it's still going to be x over 3, but now our limits are from 3 to b. And so when we evaluate this integral, we have 1/3 tangent inverse of b over 3 minus 1/3 tangent inverse 3 over 3, which is 1. So when tangent is the angle whose tangent value is 1 is pi over 4. So what we have is 1/3 pi over 4. And I don't know if you remember how the graph for tangent looks. We're going to scribble this off to the side for a moment. So remember, tangent has asymptotes at the odd multiples of pi over 2. So if this is pi over, so we're going to have pi over 2 right here, and we're going to have pi over 2 right here. So we have vertical asymptotes at that point, and the graph of tangent looks like this. So that when tangent gets close to pi over 2, your value goes to infinity. So the other way around is going to be that if tangent inverse is going to infinity, it means that this angle is approaching pi over 2. So what we have is 1/3 times pi over 2 minus 1/3 times pi over 4. So basically this is pi over 6 minus pi over 12, which is pi over 12. So this improper integral converges to pi over 12, and that directly goes into part B. So what we could call this is the integral test. And remember, for the integral test, if the integral of the sequence converges, then the series that has that sequence also converges. So in the case of B, we would say convergent just by an integral test. So your work for part A is your justification for part B. Because this integral converges to pi over 12, then the series, we can go ahead and write this down. Because the integral converges, then from n equals 3 to infinity of 1 over n squared plus 9, this is also convergent. Now, it doesn't converge necessarily to pi over 12, but it does converge because the integral itself converges. So then for part C, we have to determine if the series from n equals 1 to infinity of -1 to the n of n squared plus 9 over e to the n converges absolutely, conditionally, or is divergent. So we know this is an alternating series because -1 to the n, the signs is just going to change because of the -1 raised to the n power. So remember, for the alternating series test, the terms have to alternate in sign. That's true. 2, they have to decrease in magnitude. And that's also going to be true for this one. E to the n grows larger than n squared. If you ever run into, you could use the ratio test to verify this, but just having good number sense is going to tell you that e to the n is going to grow larger than n squared. So then for number 3, we have to determine if the limit of this sequence is 0. So the limit when n approaches infinity of n squared plus 9 over e to the n. The -1 doesn't really matter because we can just do an absolute value. So when n goes to infinity, we have infinity over infinity because both of these actually go to infinity. So this is going to be a case where we can apply L'Hopital's rule, which we're just going to put L'Hopital here. And by applying L'Hopital's rule, we get the limit as n approaches infinity. That's going to be 2n over e to the n, because for L'Hopital's rule, we do the derivative of the numerator divided by the derivative of the denominator. And so if n goes to infinity, we still end up with infinity over infinity. And so we can apply L'Hopital's rule again and get the limit when n goes to infinity of 2 over e to the n. And so now we end up with a number divided by an expression that's going to tend towards infinity. So that limit is 0. So this series is at least conditionally convergent because it passes the alternating series test. Now the test for absolute convergence would be if we have, so we're going to put conditionally convergent, and then the test for absolute convergence is looking at the series from n equals 1 to infinity of n squared plus 9 over e to the n. And so since we know the ratio test, we can verify this pretty easily. And so we're going to say by ratio test, what we're going to end up with is, we're going to like slide this in down here. So by the ratio test, we would end up with the limit as n approaches infinity. So remember, for ratio test is an plus 1 divided by an. So that's going to give us n plus 1 squared plus 9 over e to the n plus 1. And then we just multiply by the reciprocal because that's the an term. So we end up with e to the n over n squared plus 9. And we can rearrange our terms. So we end up with the limit when n approaches infinity of n plus 1 squared plus 9 over n squared plus 9. And then we end up with not plus, but times. So the e to the n over e to the n plus 1 is just going to be 1 over e. And for the ratio test, this is going to be convergent if this limit is less than 1. So if you expand this out, you would have n squared plus 2n plus 1 plus 9 over n squared plus 9. And for this part of the fraction, when n goes to infinity, you have an n squared divided by n squared. So this limit is 1 times 1 over e, which is less than 1. So by the ratio test, this thing is absolutely convergent. So for C, we're going to say our result is absolutely convergent. And again, we use the ratio test. There are a couple of other tests that we could probably use. Root test, because we see this thing right here, the e to the n, but that's not necessary. Ratio test is pretty good for a lot of things. For number 2, we have this problem where we have -1 to the n plus 1 times x minus 3 to the n over, I'm sorry, you can't see that. So we have -1 to the n plus 1 times x minus 3 to the n divided by 5 to the n times n to the p power. And for part A, we want to know for p equals 3, x equals 8, does the series converge absolutely, conditionally, or diverge? Let's write this down so we can see it. So we have the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 3 to the nth power divided by 5 to the n times n to the, is that p power? Sure. And in the case of p equals 3 and x equals 8, so if p equals 3, so we're going to put in p equals 3, x equals 8. What happens is we end up with the sum from n equals 1 to infinity. So if x is 8, 8 minus 3 is 5. So we end up with 5 to the n over 5 to the n. So we're going to have -1 to the n plus 1. Now again, if x is 8, 8 minus 3 is 5. So we have 5 to the nth power divided by 5 to the n. So that's going to be 1. So we end up with -1 to the n plus 1. And p is 3, so over n cubed. So this is an alternating series. And this is going to we'll just look at the 3 conditions for the alternating series. So clearly these terms alternate in sign because of the -1 to the n plus 1. They clearly decrease in magnitude because as you divide by a consecutive cube, as you divide by a larger cube, the terms are going to get smaller. And because the terms get smaller, in this case, because we have n cubed, that limit is going to be 0. So just by looking at this, you know it passes the alternating series test. And if you have to write some work to verify that, you can say 1 terms alternate sign, 2 they clearly decrease in magnitude, and 3 the limit when n tends to infinity of -1, well, we can just have 1 over n cubed. That limit clearly equals 0. So this, at least, again, is conditionally convergent. Now, for absolutely convergent, we just have to look at, we need to look at the series without the -1. So from n equals 1 to infinity of just 1 over n cubed. And this is going to be convergent by the p series because p equals 3. So p equals 3, and that's going to mean that we get absolutely convergent by p series. So that's it for 2a. For 2b, for p equals 1 and x equals 8, is the series absolutely convergent, conditionally convergent, or does it diverge? So all we have to do is, so x is still 8, so we still end up canceling all of this stuff out and end up with -1 to the n plus 1 over. But for part B, p is 1, so we just end up with the harmonic series. And so the harmonic series is conditionally convergent. Well, the alternating series -1 to the n over n, that's conditionally convergent. And then the test for absolute convergence when p equals 1 is going to be divergent. And remember, we showed this by using the integral test where we ended up with the natural logarithm, which slowly goes to infinity. So for part B, we have conditionally convergent. The test for absolute convergence fails because p equals 1. And then for part C, when x equals -2, for what values of p does the series converge? So if x is -2, so for part C, we have the series from n equals 1 to infinity of -1 to the n plus 1. Now, if x is -2, -2 minus 3 is going to be -5, so we get -5 to the n. So we have -5 to the nth power over 5 to the n times n to the p power. So we can do some fancy algebra here. So -1 to the n plus 1 is equal to -1 to the nth power times -1. And then since we still have this -5, we're going to rewrite this as the series from n equals 1 to infinity of -1 to the n. And we're going to slide the -5 to the n over and put the -1 over here. So -1 over 5 to the n times n to the p. I don't know why I wrote the p so large. So p. So -1 to the n times -5 to the n is equal to -1 times -5 just to the nth power. So this is just 5 to the n over 5 to the n. So all of this cancels. So we have this series from n equals 1 to infinity of -1 over n to the p power. And so for what values of p does the series converge? So now we're looking at an alternating series, which is going to converge, like this is going to converge for p equals 1. Yeah, so just p just has to be greater than or equal to 1. Now we're looking at just 1 over n to the p is going to be convergent if p is strictly greater than 1. But because alternating series can be conditionally convergent, we're going to have p has to be greater than or equal to 1 for part C. All right, so guys, I'm going to break this video into 2 different sections. We just covered the free response. So in the next video, we will pick up with the multiple choice.